Okay, I'm going to start now. Good evening, everyone. Welcome to the first session of GDSC AEC for the session of 2021-22. I welcome you all on behalf of our team, and today we have with us someone very special, a senior scientist from ISRO, Dr. Santonu Goswami, sir. We are very glad and honored to have you with us today, sir. We hope this session will be as enjoyable to you as it is for us conducting and being a part of it is. So, sir, over to you.
Okay, thank you. Can you hear me well?
Yes, sir.
All right. So yeah, I'm glad to be here. I've been working with AEC students.
Sir, you have been muted.
Sorry, yeah. Can you hear me well now?
Yes, sir. Yes, sir.
All right. So when you told me about this, and when you actually Subrot also, I think mentioned about this platform. So it was of my interest to come on over and talk. So yeah, so it would have been good to actually give an introduction about the forum as well, because I'm not quite sure about the forum. Maybe after a talk you can just give an introduction. That would be
Yes,
good.
sir, surely.
Because I'm assuming you have students from Assam Engineering College in here.
Yes, sir.
Probably from all years and from all disciplines, correct? From all
Yes,
branches,
sir.
right? All right, okay. So let me share my screen. Okay, so can you see it?
Yes, sir, it's visible.
Okay, so it's a general audience, and so that's how actually I thought I'm going to look at, because you guys are coming from an engineering background, and I thought a general interest is going to be on data. So I said, why not talk about data, right? Let's talk about data today. So it's a very general talk. I'm just going to give you an introduction about what I do. It's a very brief introduction, and then discuss about data science in general. I'm not planning on getting into any direction. I'm not planning on talking about any basically topics or anything. But it's a discussion that I thought I'll have with you guys to see, or to actually hear back from you guys, maybe some of the interest that you might have, and maybe we can have more interaction over time. So first of all, don't worry, I'm not going to bang my drums about what I do. So it's just, again, as I said, just a very brief introduction. So just the introduction of the concept, and I just hope I don't bore you too much, right? When I do this. So before, again, it's I'm talking to a group of students, and I'm working as a senior scientist now. But how I got in here, it's probably something that some of you might be interested to know, right? So I was a physics student before. That is when I started in Guwahati University, and then physics is tough, right? I mean, it's not an easy subject. So I did my MSc in physics. Then I went to University of Texas at El Paso for my master's in physics, because as a science student, when you go for higher studies in US, you lack 1 year, so you cannot really get into a PhD. So you need to actually do an MS again. So I go in there, I read, basically start from the same textbooks, right? Same physics textbooks, but different professor. But physics was very different when I started there. So it's kind of what will strike me is, okay, wow, it's same subject, same books, but the approach is different. So when I was thinking about doing my master's thesis, I said, why not, like try to do a thesis in physics education about how to teach physics. So that's what I did during my master's. So one thing I learned was that it's take home message or like key point from that from the journey was, when you are going to talk about a concept, when you are going to talk about or when you're trying to teach, you need to use the simplistic language that you can and avoid all the jargons, because that's how you can actually send the message across, right? And like, and then I did some teaching after that master's degree, and then I wanted to get into a PhD. So I had option of getting into nanoscience or environmental science and engineering. I opted for environmental science and engineering, so completed in 2011. Then I have worked very shortly as a postdoc scientist in Michigan State University, and then another postdoc scientist in the Climate Change Science Institute at one of the national labs, Department of Energy, and then research scientist in the Center for Urban Sciences Progress we had completed in 2016, and I joined here as a senior scientist in ISRO in 2016. So I continue actually working. So how I evolved with physics, right? And then obvious choice was getting into a similar physics, which is what I was looking at into nanoscience PhD. Then I happened to be in a seminar by a professor, which was in the seminar was on environmental science and engineering, basically using tools and technologies about asking some questions of climate change importance. So it really got to me, and so I say, what, I'm not going to do nanoscience PhD. So I moved there with environmental science PhD, or like PhD, and that got me into climate change research. And then I moved on. Basically, after my climate change studies, I had this great opportunity of working in urban domain. So got more and more data intensive, and like that's how I got into this data science field. So this is the my data science journey so far. It's so for me at least so far, it's all about solving a problem, right? So that's how I look at it. And what I do now, I do climate research, and I adopt a data-driven approach. I ask questions of relevance or importance in natural ecosystems, and to understand, climate change impact.
So you've been muted out. So please check.
Can you hear me now?
Yes, sir. Now it's working.
Yeah. So as you know, this climate change is a problem that's happening on the planet because of the changes in carbon dioxide or other greenhouse gases, which is causing the temperature to go up and also changing the weather patterns. We are starting to see like increasing frequency of weather events. So being able to understand these patterns, being able to predict these patterns, and being able to develop solutions for adapting and mitigating to these problems is of importance. So I am somewhere in the domain because I don't do everything. So currently I'm working on two things, two areas. One area is how the coastal ecosystems in India are changing and what are the drivers of change. And I am carrying out this study using long-term remote sensing and climatic data. So, to understand things such as some of the erosion and like accretion patterns are changing, in climatic in Indian coast. How some vulnerable coastal ecosystems such as Chilika Lake, they are experiencing changes over time. Here on the bottom right corner, you see those green, bluish thick patterns. Those are actually invasive species taking over this ecosystem, so which impacts the overall stability of the ecosystem a lot. So this is one area of study that I've been working on, which are focused on Chilika, but I'm also spreading across other parts of India. The second part that I have been working on, and this is an area that I've been working since 2006, which is to understand the climate change impact on the permafrost landscape. And today, actually, because it's a new area for you guys, so I thought I'll just show a few slides in here only, because it looks quite interesting when you see the amount of changes there that you even see from naked eyes, right? So permafrost is a frozen landscape, frozen soil, which is about 23% of the northern hemisphere, as most of this pattern is concentrated in the northern hemisphere, like in the higher latitudes. In the Himalayas, we do have some of these landscapes present, but we haven't studied that much, so we don't know how these landscapes are actually, or this landform is behaving, or what is the current state of this landform in terms of climate change. So this is what the permafrost landform is all about. Here you can see the arrow that is pointing in here is called seasonal active layer. So basically what happens, these latitudes, they are very cold areas, so they remain frozen most of the year. And during the summertime is about 2 to 3 months in those areas. The snow goes away, top layer it thaws, or you can say melt out, right? Then the soil becomes available for all the growth activities, right? But the frozen layer, which is underneath, which is actually the permafrost, which remains frozen. And this white stuff that you can see is actually like a chunk of ice that is sitting in here. It's called ice wedges. And why it's important? Because this permafrost landscape contain about 30% of the world soil carbon. They are frozen, and their plant mass is very, very small, about 1%. Land area is about 9% in there. Productivity is very low, but overall soil carbon is about 30%. So if these landforms are going to thaw away, then this is going to create a lot of greenhouse gases coming out to the atmosphere, and that is going to warm the atmosphere more. That means this is going to create a rapid increase of the climate warming. So that's a very important area, a very interesting area for the overall, the community. So even though people have been working in this for a long time, our knowledge about this landform is increasing, but not to the level that we want it to be, because we are still trying to find where where this landform. You can say we don't quite know the overall extent of this landform, and then the overall disturbance that this is having. So we do have models that predicts about how these landforms are going to change, and what is the overall impact on the local to regional climate. But there are high level of uncertainty in that. So again, this is a very interesting picture I'm just showing in here. So it's when these landforms they degrade, what happens? It's a big chunk of ice, or basically soils. They just gets detached, right? And they just keep basically degrading like this. So when this stuff they degrade like that, it becomes a hotbed for the greenhouse gas that comes out to the climate, right? So to understand how these landscapes are changing, we need to generate data, multi-year data, monitoring data on these different parameters, we call bio-geophysical parameters for this landscape at the ground level, and also from remote sensing data and satellites. Because remote sensing, what it gives us a understanding of this landscape, or any landscape to be honest, at a much larger area. And we cannot go to the field on a regular interval, mainly because it's expensive and sometimes it is impossible to go. But our remote sensing satellites can actually take the data continuously for this landscape. So it provides a lot of very, very valuable data. It's a plot that I'm showing out here. This is the spectral plot of a vegetation, green vegetation. I'm showing these, as you can see, these numbers called PRI, the NDVI, WBI. These are called spectral index. So remote sensing scientists, what they do, they actually look into some of the absorption features of this plot. It can change for different land cover. I'm just showing for green vegetation. Each of these index means something. NDVI means how physiologically active, how productive this vegetation is, how much photosynthesis is going on, you can say. WBI, water band index, is how much water is inside the plant. There are some, like very juicy plant, and there are like dry plants, right? The overall, actually, they control the overall fluxes of these ecosystems. And PRI is photochemical reflectance. It's kind of a higher level stuff. It's how they reduce the stress, or how it's a measure of how stressed the plant is towards temperature, light, etc., like that. So it's a glimpse of some spectral index which people use to actually exploit the remote sensing data to study these ecosystems. So we have done experiments in the Arctic to understand the climate change impact on these permafrost landscape using a very highly instrumented sites. So we have built a large instrumentation like this. It's a robotic tram that had, we put actually a automatic robot in here. We put the hyperspectral sensor and other sensor in there. Then we just turn it on. It goes by itself across the length, and it collects hyperspectral data at every point, right? So we had 3 of those sitting next to each other, and we actually changed the hydrology of the lake. So we're trying to see how the changing hydrology has an overall impact on these ecosystems, because 3 different hydrological changes means 3 different climate change scenarios, right? How they changes. So we basically generated our own data, and so it's like an example about how we use this data to get insight from the data. When here I'm showing you these 4 different pictures from the beginning of the season to the peak season, and how these plots they change, and how they can tell us how these ecosystems are changing. It's from this particular data, which is hyperspectral remote sensing data. And on here, on the right bottom one, you can say these reflectance bands are converted to a number called NDVI. And as the season progresses, this value goes up. This DOY means day of the year. It's basically the Julian day, right? So again, that's a study that we have done in the region, like a local scale. Then using remote sensing, or basically geospatial analysis, we have also carried out study to understand how these permafrost landscapes they are changing over time. So this is a study that we did in collaboration with the research coordination network of permafrost, where we estimated that these permafrost landscapes are having the disturbance of these permafrost landscapes is actually the top feature that I showed in few slides earlier. What is the extent of this disturbance in the overall permafrost landscape for the northern hemisphere? So we measured that, estimated that, about 25% of these landscapes are seeing this have this disturbance feature basically, right? Then we can also actually look into features as how some of these landscapes are changing, are greening up over time. This is a picture or analysis from Svalbard, near Eastern Svalbard, and we were trying to see what is the pattern of greenness for this particular landscape using 250-meter MODIS data, which is MODIS is a satellite from NASA for the last 17 years, actually, from 2017. When the data was available. So there are lots of this sort of data that is coming out now. So when we want to know the climate change impacts, or we want to study this climate change overall ecosystems, so we need to study these ecosystems at a very different scale. Otherwise, what happens if we are going to do a study just from the satellite, which is about say 100 kilometer scale? We do not know what is happening at a finer scale. Say in here, this is a very typical study that we are carrying out. It's called OTC, object chamber. This plexiglass stuff that you see. If you leave it out there, it gives the inside temperature about 1 to 2 degrees higher compared to the surrounding. So if we leave it like that, so basically we are warming up that plot, and how that warming has an overall impact on that particular that small plot. It's actually not even 1 meter, you can say 50 centimeter like that, right? But then that is at the finer scale that you can do. Then how do you connect from this 100 kilometer to 1 meter or 1 meter to 100 meter? Because there are lots of different scale at here. So we just start basically bringing in these different instruments. This is the robotic frame, which is scale is about 100 meter, 100 to 200 meter. Use drone, which is about 1 kilometer maybe, right? And then use plane. We put sensors out there, which is maybe about say tens of kilometers, right? So we need all this data to understand how these ecosystems are changing over time, and how these understanding can help us to model these ecosystems towards future changes, right? So these myriads of platforms are helping us to collect this data, and this as we are improving this data, we are improving our methods. We are starting to get more and more data being collected, which is actually really helping us. Then the question is, with so many more satellites coming up now, with so many more other instruments, that are collecting data, we are right in the middle of a data tsunami. I'm talking about just this ecosystem or climate change research, not even talking about the other side of things, right? So when we have this data tsunami, we had this problem of archiving the data. We kind of got our handle on about that. But then how do we process this data? In the hyperspectral data, we have 256 band. Band means that different spectral resolution. We get that information, but we don't use that. It's a dimensional reduction problem, right? When we use spectral band, indices, we just use few bands. But we are just throwing in the rest of the data, right? In here also, it's a picture from Landsat satellite, right? Which has been actually flying for the last 40 to 50 years, by NASA. So it's giving us so much more data. Then there's Sentinel is there, MODIS is there, Virus is there. That's basically hyperspectral sensors being flown over from satellite. More and more data is just coming in, right, from the satellite, I'm saying. And then you have all these ground sensors. Then basically all the other sensors. It's coming in right now, right? So as we are getting busier processing this data and asking questions, or basically being happier on one side because we have more data right now, right? We don't really have to stress out saying that we don't have data. But then we have another problem. So we have more data than we need in many cases. So what else can we do about it, right? So as these artificial intelligence and machine learning and deep learning field is coming up again, right? And we probably have an opportunity out here to use the intelligence from these like methods to gain a better insight than our traditional methods, right? So we have this ever-increasing problem of climate change. Then United Nations, they are setting up 17 sustainability goals to be achieved by 2030. So from this year, there is ecosystem. I think UN is calling it ecosystem restoration decade or something, right? So I mean, how do you actually use these powers of data and new methods to help us achieve some of these things? But the question is, I mean, what is working and what doesn't work? I mean, we don't know about this quite yet. So we are just starting to scratch the surface. So we are just clustering data. We are trying to find pattern, right? So that's how we are starting. But we got to have a start, and that's what actually we are starting. But I think there's a lot of promise in here. So now moving on, let's talk about the data science in general, because I'm assuming as engineers or as like people who might have an interest in building a research career, maybe, or getting into this data science field. This should be of interest to you. Again, I'm not getting into any specific topic. I'm just going to talk about how this field is shaping up, right? So when you talk about data science landscape, I just Googled it in data science landscape. So this is what it gives me, right? You can see how busy it is, right? But there is like a pattern though. On the left side, this is infrastructure. Right in the middle, it is analytics and machine learning intelligence. And then this is applications, enterprise applications, right? So data engineering, data science, and applied ML, you can say, or applied data science, right? But then you look into all these different things. Like there's so much stuff that is out there, right? Where do you start? That's a question, right? I mean, how are you going to learn all the machine learning algorithms, or I mean, how do you start on this, right? So that's probably, if you haven't started, that is probably the first thing that is going to come to your mind. And another danger is there's so much material out there, just like data tsunami. It's almost like tsunami of courseware in data science now, in machine learning, in deep learning. And a lot of this stuff are actually coming out free, which is excellent. But then where do you start, right? So that's something, I guess, there's not an answer to it. You just probably find a pivot point. You just start with something kind of classic, and then you probably move in there. So data, by the way, I mean, what do you mean by data? Data is what? Data is just facts, right? Individual facts of statistics or item of information, right? So numeric, right? Data collected through observation. So again, these are actually definition I'm getting from this document. It's not that I'm writing it. In a more technical sense, data are a set of values of qualitative or quantitative variables about one or more persons or objects, while a datum is a single value of a single variable, right? It's kind of complex, isn't it? I mean, the definition they're giving. And then when you type data, you start seeing all these cool pictures, right? So it's, again, this is how things are being projected to, or being basically given to you. So how do you filter this stuff into something that is comprehensible? So you always need to learn how to filter out information to keep it in a simplistic form. So, I mean, to me, data is just a representation in a quantitative or qualitative form, right? That is what data is all about. That's what I'm going to remember. So again, I mean, what is data? Here, do you see this is basically mixture of some images right here. These are two separate images over the coast of Chilika, over the coast of Orissa. And these different colors, they mean something. They are actually sedimentation, right? you see, in the river, there is red color. That is a high sedimentation when it's red, right? And you can see the water is coming out. This is very high sedimentation on this. This is data by itself. What about this one, the one on the right? This is a picture of, it might be from US, or I don't know, maybe from even Bombay. I have no idea. It cannot be from US. It has to be from someplace like India, because there's a highway that's going through, which is ocean, like a sea, right? There's a little beach out here. On the right-hand side of the highway, very nice buildings. On the left-hand side, this is a slum, right? It's a very interesting picture. It's just some data, right? This is the Wikipedia picture, right? Wikipedia page, History of India. This is data itself. And this is on the lower bottom. This is a picture from Hyderabad that I actually, took it this morning. It shows the traffic condition in Hyderabad, right? All different data, correct? So that I'm speaking that you're, this is also a data itself, correct? So if you now think about, combine all this stuff, right? So data science, it's a mixture of statistics, machine learning, and some domain expertise, right? So it comes from basically your data processing, computer science, mathematics, and statistics. So data science, it encompasses all this stuff, right? So it's a very broad term. So one thing, if we are going to talk about data science, so something that we might get lost at some point, like this data science, machine learning, AI, cognitive science. This is like climate change. Climate change happened in this world earlier as well. It, it just went up and down, things like that. But now we are more worried because we have, the human civilization in here. Just like that, machine learning started a long time ago. You went up, then then there is a cooling period. Then you went up again. Then there is a cooling period. Then from the that in the 2000s, it's just going up again, right? So there are certain hypes about it. There are some actually hopes about it, and there are some fears about it, right? So again, this is again a timeline about this AI, artificial intelligence timeline. So the first book on machine learning I found was from the 1962 or something, right? And then with the emergence of this, then we are starting to see the emergence of big data. I've shown an example from climate science, right? So now, as I said, there are hypes, there are fears, there are anticipation about this field. So I guess we should look into what one of the industry leader is talking about it, right? He's Andrew Ng, which everyone definitely know. So he's talking about the two winters in AI, that he's saying the first chill occurred in the 70s as progress slowed and government funding dried up. So another struck in the 80s as the latest trend failed to have the expected commercial impact, right? So funding was the first time. The second was actually commercially, it was not, viable, right? And then he also says that AI systems will only become more powerful. This might not only increase the accuracy of existing deep learning tools, but also allow that technique to be leveraged in new areas, such as parsing and generating language. So there is definitely hype, but I think there is such a strong underlying driver of real value that it won't crash like it did in previous years. So we can, if we think about it, how the overall ecosystem is growing. Of course, there are numbers saying that there will be these many millions of jobs in data science. There is somebody is going to say that data science is cooling down and all these things. But you have to think about what is going in the overall ecosystem, right? So this cloud, these computers coming so strong, right? in like a lot of industries are starting to adopt these data science, machine learning sort of concepts. A lot of them are actually starting to see useful in cost cutting, efficiency, etc. Right? And I think when a movement like this is happening, you just only can be hopeful and not look at the negative side of it. Because if we see ourselves in this current movement, we do feel the excitement, and we do see how, from our current knowledge, we see how things are moving forward, and that probably also reflects into the number of jobs that are being created, right? Of course, there is always a thing about a field being developed, right, where number of actual skills or people with solid skill set are going to be a subset of the people they are going to be in the field. So you guys need to think about how we can be in that smaller subset, people with strong skills in data science field who are going to be sought after, right? So before I end, I thought I'll just talk about this. Like as I said, it's kind of I try to talk about. Like, yes, this is machine learning. Yes, this is deep learning. This is very exciting stuff. But how to say it in very simple terms, right? Because at the end of the day, this is statistics. You're using computing, yes, but at the end of the day, you're trying to solve a problem. So if you don't understand, how do I say? Let me see. If you don't get these concepts in easy terms, you may not have enough time to understand the problem that you are trying to work on. And if you cannot connect your knowledge to the problem, then it will be difficult for you to actually solve the problem, right? Again, machine learning type of thing, there are two ways you can look at it. One is you can become the researcher, right? It's just developing algorithm, like from the scratch up, like young Goodfellow, right? Jeff Anton. Or you can think yourself in the applied domain where you are using these tools to actually solve a problem. It's like I was telling somebody, I think yesterday or the day before, it's like you get to the kitchen, you're trying to cook a recipe, right? You don't need to know everything about your gas stove or your microwave. As long as you know how to operate the microwave, you can cook a good recipe, right? So again, just along that line, I thought I'd just pull up definition about machine learning, from the web. It might have picked up from IBM page, Microsoft page, like that. I don't know which one as well. So it's a machine learning is a branch of artificial intelligence and computer science which focuses on the use of data and algorithms to imitate the way that humans learn, gradually improving its accuracy. It's a clear definition. Same in here. I'm just not going to actually read through this, right? And then I think the third one is from Wikipedia, right? It says ML is the study of computer algorithms that can improve automatically through experience and by the use of data, right? So, these are fine, right? But if you are going to go through this definition, this is like trying to memorize something that somebody else is, telling you something that you are saying, okay, let me memorize this stuff, things like that, right? So, and then, oh, wow, okay, look at this. This is kind of scary. Like, you think about machine learning, that, like think about all these different branches. It gets into like very complex thing, but of course it also shows, like what the application is right here, right? I just wanted to throw this out there, how things can get complicated. So to me, machine learning is just a labeler, right? It's an approach to make a lot of small decisions. It's like the cat or the dog kind of problem, right? So that's how I try to remember it. Like point is, keep things simple, right? Try to simplify stuff, and then like try to understand, why things are out there, right? So again, like in a, I guess one more thing before I even finish. So the difference between machine learning versus traditional programming is, in traditional programming, you get an input, you do the manual coding, then you get the output. So it's like, I want to find this, so that's why you know what you're going to do, right? In machine learning, you have the data. Basically, input is the data, right? You know what the output you want. You know what recipe you want. And then you try to find the best, like ML model, so that you can learn from the data, and you just try to figure out how to find it, right? So again, this is the life cycle data science project. I'm not going to go through this. Or maybe I should. I am not going to go to this. So these are some recommendations from me if you're starting the data science journey. You guys might have on the way already. Try to take a course, like maybe a free course actually, or you can always audit a course in Coursera. I think there's a good course in analytics Vidya right now. Okay, I'm putting this. There are several free courses out there. They always come up with a comprehensive learning path to become a data scientist every year, right? So that is over there. You'll find a lot of actually, these free resources. There's one more course out there that just I saw it. I think they are releasing a few days ago. And then Andronang's machine learning course. It's a classic in Coursera. You can do free audit. And I think for India, the scholarships are available as well if you want to get the certificate. Right? There's no end to this list. So I follow popular YouTube channels. Krishna is a good one, right? And IBM, I think they have a paid certificate that you can take a course. But yeah, I mean there are lots of resources. But if you start one, just finish it. So and then get into these competitive platforms, right? Kaggle was the original one, but there are a bunch of them out there, right? And as you're doing this, I think the most important thing is read a few research papers, right? If possible, do an actual research project if you can find, basically if you can do it, right? And if you can publish a paper, this is really going to put you in the next level. Because as a data scientist, you become a storyteller, right? You're a storyteller and you exploit statistics to gain insight from data, right? If you don't know how to read a paper, if you don't know how to write a paper, then you are an incomplete data scientist, right? So that's something that you should think about it. You should take it seriously, right? And then again, I mean, think about that curve, right? The one that I showed you, right? Try to think about a business problem, right? And try to figure out how to find a solution using ML, because that is the business out there. That's the main thing that you will be doing as a data scientist. Some business is going to, some industry or some companies are going to hire you into the data science team. They will say, find do something for us, right? Or they might be throwing it, several problems out there. Say, okay, find a solution for it, find a solution for that. Most of the time, they don't really know, what problem they want to solve, right? But in general, they can say cost cutting, right? And, increasing efficiency, sort of things, right? So try to think about it. Try to think about, try to learn about these problems, business problems that are out there, right? And how people have used machine learning type of thing maybe to solve this, right? So this is I'm just saying it. Start early about this. Don't get lost in Python and R coding. That is the tool that you must know. And I don't think, that is something to worry about as an engineer, right? An excellent engineer, you guys will know it. But if you don't know how to think about data science properly, then the journey might be longer, right? So anyway, so point is, there is a data tsunami, I think it's very exciting, but are you ready yet? That's the question, right? So yeah, I'd love to hear from you about your interest and all. Get in touch if you want. So that's it, Gayatri. I mean, that's all I wanted to say. If anyone has any question, I mean, I'd be more than happy to talk about it.
Yes, we'll open it up for the questions now.
Right.
If anyone has any questions, please feel free to turn on your camera and ask, sir. And I'd also like to add that your questions don't really need to have to be technical. Anything like about
anything.
or
I'm actually
anything you would want to ask.
Right. I mean, I want to know. I mean, I know some of you people because I've been working with some of you. But in general, what is your interest in data science? So that's what I guess it'd be a good thing to talk about, right? It doesn't have to be connected to the PowerPoint. It can be any discussion, right? Or maybe I should start asking questions. All right.
I think we are done here. No questions.
I guess everything is very clear about it.
Yes, sir. I'll just request everyone to turn on your cameras. We'll take a group picture, and yeah. Yes, done. There's another exciting addition. So I'll just introduce our club before we leave. So as you all know, Google Developer Students Club is a community of students where we don't really only focus on coding and the core hardcore engineering stuff, but we also focus on our research team and a lot of different things that come under a technical umbrella. So we have students from various domains and departments who contribute with us, work with us, and we together take on projects which we are excited and interested about. As a new session is going to start, we are taking in new members. So since you guys have been with us till the end, I'm releasing the form for membership in the messages. If you would like to join us, please do fill in the forms and we'll get back in touch with you. So yeah, the form is in the messages of this call. So feel free to fill it and join us. So I hope today you guys had a good session. It was a productive hour for you. It was great for us. It's always good hearing, sir. So yeah, I hope it has been good for you too.
I'm happy to come and talk. So it seems like a very nice platform, and best of luck to all of you.
Thank you, sir. So it's purely technical. So
yeah,
all technical people here.
Right. Yeah, I understand. Yeah. That's great. All right.
Thank you.
I think I can exit.
Yes, sir. Thank you so much for being here with us today.
Thank you very much. Thank you.
Thank you for your time. Thank you.